Because try it. Take the derivative of cosine x, it's negative sine x. Then make it negative, that'll give you positive. What are some other ones you would know? Should know. What's the antiderivative of secant squared x? Yeah. Just tangent. Just tangent. Right? Because derivative of tangent of x is secant squared x. Now, if you refer to your formula sheets that you're allowed to print on the test, right? Who has those with them? I want to refer, can I borrow yours real quick so I can tell everyone what page it's on, whoever has it? You may not have all of them. You got them all stapled here? All right, so if you look at reference page 6, it has all of these. Now, I still need to show you what this notation means, but just for right now, just know that reference table 6 is where all these things are going to be. Yep. As I need to introduce that before I can refer you to that. I forgot about that. All right. Now, that's as far as we're going to go right now with the antiderivatives, just with this. Now I'm going to try and introduce you to something, a kind of a different concept. Riemann sum. I don't know if that's R-E-I or R-I-E. I forget. Riemann sums. All right. How many of you have ever seen this symbol before? Sigma. That's a Greek, that's the capital Greek S, right? Capital Greek S. Now, does anybody know what it stands for or represents in mathematics? A sum. Okay? That's the symbol for a sum. How many of you knew that? So, I mean, just show of hands. You knew that was a symbol for sum. Okay. That, whenever you see that symbol, it means you need to add things up. Okay? Technically, the way I do it is something like this. I'm just going to make something up. K squared plus 1. And I'm going to put what's called an index here. K equals 1 to 3. So the way it would work is this. You start at 1. Okay, the bottom of that sum, k equals 1. I start at 1. I plug 1 into that expression. What's 1 squared plus 1? 2. Then I add to that. Now I let k be 2. So I increase the number by 1 integer. So k goes 2. Now plug 2 in. What's 2 squared plus 1? 5. Plus 3 squared plus 1, 10, right? You add those up, you get, what, 17? So this sum right here gives you this number, right? Got the basic idea? Now, you can have a sum that's finite, like this, or you can have a sum where you start at maybe 1 and you go infinite, which means you add things up forever. And here I'll give you an example of something you could add up forever. How about 1/2 to the k? 1/2 to the k. So let's start at 1. What would you get? 1/2 to the first power. Plus, now let k be 2. 1/4. Now let k be 3. 1/8, 1 what? 16th, plus forever and ever, right? This would keep going. Here's just a question to you. If you add things up forever, is it always going to be unbounded? In other words, like, If I were to take, let me put one right below this. K equals 1 to infinity of k. That would be 1, then I add to it, let k be 2, 2, let k be 3, 3, k be 4, 4, and I keep doing that forever. Let's label these A and B. They're both infinite sums, aren't they? Which one of those obviously is unbounded, like just becomes infinitely large? The second one, B, right? 1 plus 2 plus 3 plus 4 forever is going to just go to infinity, right? What about the first one though? What about A? Will A actually keep getting bigger as I keep adding, or is it bounded? Is there a limit to what that adds up to be? Each one of the pieces is close to 0, but it's never 0, right? This is a big, like, theoretical kind of question. Look at A. This is a very important thing. Cal 2, this is what you talk about, this part of what's called sequences and series. Right there, part A is called an infinite series, or a series. And what you do in Cal 2 is you actually figure out if that adds up to something or not. In this case, I'm just trying to ask you the general question. Do you think that adds up to something or not? Yes? Do you think it keeps getting bigger, or do you think that there's a cap, like it doesn't get past a certain number? Each one of those, you think it's approaching 1, but it never gets there? That seems to be... Yeah, you can do it with like a cup, right? Imagine you have a cup, and the first thing you add to it is you fill it halfway, right? And then the next thing you do is you add 1/4 of a cup to it, right? So now that puts you up here. So there you've got your 1/2 with your 1/4 on top of it. Now you add 1/8, which is half of that, which puts you up here now, right? Then you add 1/16, which is half of that. And you keep doing that forever, don't you? You'll never overfill this cup. Which is really kind of a troubling thought sometimes, because what you're saying is that each one of these individually is a positive number, right? Guaranteed, each one of those numbers is positive. They are all bigger than 0. Yes? So you're telling me that if I take a positive number and add it to another positive number, and I keep doing that forever, that it's not going to become overfilling at some time? And the answer is yes, it will not. In some cases it overfills, in some cases it doesn't. So you study that in calculus too. It's called convergence or divergence. A here converges, B here diverges. Now, I'm getting a little sidetracked because what I'm trying to get you to look at right now is this stupid symbol, sigma, okay? Because the symbol is what's important here. All right, so now here's where I'm going to try and bring the symbol back to earth here. We have a function. Imagine we have a function, and we take it from one endpoint to another, and we want to figure out what the area underneath that is, right? What's the area underneath that function? No idea, right? No idea. What's one way we could approximate it? And let's act like we actually have the function. Like, I'm making this up completely. Like if we had the function right there, and let's say this point was 1 and this one was 2. How could we approximate the area underneath there? What geometric objects are you comfortable finding areas of? Rectangles, right? Rectangles and squares. Rectangles are just as easy as squares, right? So how about this? How about a really, really bad estimate like that? One rectangle. That rectangle is obviously too much, isn't it? Oh, let me try something else. How about I cut that interval in half and do a rectangle that goes up here, and then another one that would go here. Well, that gave me kind of the same thing, didn't it? Didn't it? What if I go more rectangles and go to just where the rectangle hits? Can you kind of see that the more rectangles I do, the better my approximation is going to be. I'll have less error in it. Sorry, I thought I had this right here. Where's my Riemann? There it is. Well, I don't know why it's not opening up here. Give it a second. There it goes. All right, this is better. So let me drag this sucker down. Okay, so there, I'm trying to find the area underneath that blue curve, right? 4 rectangles. Look at the area right here, 6.76. So the actual area is 5.75. Don't ask me where that comes from right now. Okay? That's my estimated area with those 4 rectangles. Here's the true area. What happens if I get more rectangles? Look at the error. Look at how I'm getting closer, right, to the true area. The more rectangles I do, the better my approximation. Yes? So what would be the best approximation ever? What would actually allow me to get to the true area? How many rectangles would I need? Infinitely many. Right? Infinitely many. Which means I need a sum of an infinite number of rectangles. Don't I? Y'all kind of see that? But you run into a problem. If there's an infinite number of rectangles, how wide then is each rectangle? 0, right? So what you're doing is you're letting your rectangle's width go to 0. So this is a limit problem. You're letting something approach 0 and you're trying to add things up forever. But it's a limit. It's basically the limit as the number of rectangles goes to infinity. So Riemann was a mathematician who actually came up with formulas for these sums. And Riemann determined that, look, if you go and you cut up this interval, you pick the point on the right side, plug it in, right side, plug it in, right side, plug it in, right side, plug it in. It gives you the same answer. Well, right now, look at the area. It's 6.76. If I were to do the left sides instead, so that means I go up the left side of the rectangle, come over, left side over. This is too little, isn't it? But watch what happens as I let it go to infinity. It still converges to the right answer. And he said, all right, it doesn't matter. You don't have to go left or right. You can go right in the middle. And if you do that, as long as you go to infinity, you still get the same area. So there are ways to do these sums by hand, but it's super tedious. Well, no, you'll see it's even better than a computer. All right. All right. I'm gonna take something like x squared minus 1. Let's do that one. Right there. Let me do less rectangles. Okay, there's x squared minus 1. All right. Let me get back to my notes here. There's my drawing. My drawing sucks, doesn't it, compared to that computer one? So if I were to sit here and I come back to this idea, right, and I were to say, look, I'm going to take a rectangle in here, some arbitrary rectangle. How tall is the rectangle? Like if I'm picking some point x here, how tall is it there? It's the y value, isn't it? But isn't that f of x? Yes? So what would the area of just that little rectangle be?